Good day everyone. We have here introduction to space complexity, time complexity, and asymptotic notation. First, algorithm analysis, an important part of computational complexity theory which provides theoretical estimation for the required resources of an algorithm to solve a specific computational problem. Here we're going to analyze algorithm complexity theory. Next, complexity theory, also called as computational complexity. It is measure of the amount of computing resource, time and space that a particular algorithm consumes when it runs. Dito, kino-compute natin yung time kung gaano karami nako-consume ng isang algorithm na oras kapag na-run po siya. And space, these are the variables or data structure na gagamitin dun sa algorithm. Time complexity, the amount of time the algorithm is completed. It is most commonly expressed using the big O notation. Gaano karaming oras gagamitin ng isang algorithm para matapos siya? Next, space complexity, the amount of working storage an algorithm need. Dito, gaya nga po ng sinabi ko kanina, it is a data structure na gagamitin dun sa isang algorithm. Here, we have to know on how to calculate the time complexity. Break your algorithm function into individual operation. Calculate the big O of each operation. Add up the big O each operations together. Remove the constants. Find the highest order thing.
So ngayon naman po, di-discuss po natin on how to compute the time complexity. So first, break your algorithm or function into individual operation. So mamaya po, makikita natin sa example natin kung paano natin i-break yung isang algorithm. Next naman po is calculate the big O notation operation. So after breaking the algorithm into individual operation, that's the time po na i-compute natin si big O or yung time complexity kasi po mas madali kapag naka-break or magkakahiwalay yung mga operation. Next naman po is add up the big O of each operation together. Then remove the constant and find the highest order term. So, ito po yung example natin. Meron po tayong array with 5 elements. And meron din po tayong algorithm na ganito. Sum is equals to 0. Meron din po tayong for loop. Then, meron din po tayo sa loob ng for loop na sum is equals to sum plus AARX index of I. So, ibig sabihin po ng I, i-compute natin lahat ng elements na nandoon sa loob ng array. So, kung babalikan po natin yung first instruction sa computation of time complexity, which is to break the algorithm into an individual operation, dito po, i-consider natin na each line of code is an individual operation. So, this is the first line of code, the second line of code, and the third line of code. So, after breaking the algorithm into individual operation, let's count the big O or the time complexity of each line. So, dito po sa sum equals to 0, the time complexity is 1. So, bakit po siya 1? Kasi minsan lang po siya gamitin or ma-execute kapag kaniran siya. Next naman po, for the for loop, kung titignan natin, dahil sa loop po to, madami siyang part. Just like the increment na paulit-ulit siyang daraanan or pupuntahan. So, hatiin natin itong for loop into 3 parts. So, meron tayo ditong initialization, meron po tayong condition, then meron po tayong increment. So, for the initialization, minsan lang naman po siya mag-initialize. So, sabihin na lang natin na 1 lang po yung time complexity niya. So, for the condition and the increment, dito naman po titignan natin kung ilang beses po siyang magtatanong ng condition and ilang beses po siya mag-i-increment. So, magkakaroon tayo ng simulation dito. So, let's say na yung I na initialize siya ng 0. So, sa for loop po natin, tatanungin niya na agad kung yung condition is true para ma-execute niya yung mga nasa loob ng for loop. Kung true siya, i-execute niya yung ito pong sum is equals to sum plus ARRX index of I. So, mag-i-increment po ulit yon, then mag-ask ng condition. So, ganito pang mangyayari. So, paulit-ulit lang po siya hanggang sa yung I is mag-equal to 5. Mag-i-stop na po yung loop natin dyan. So, magtatanong po yan kung ilang beses nagamit yung condition. So, from the initialization, mag-ask po siya ng condition. Kung bibilangin po natin, meron tayong 1, 2, 3, 4, 5, and 6. So, 6 times siyang nag-ask ng condition. And nag-stop lang po siya dito sa 5. Nag-stop lang siya sa 5 kasi po false na po yung condition. So, pwede nating sabihin na the condition is n plus 1. So, paano natin nakuha si n? Let's say po na yung element natin inside the array is 5. Then, bibilangin natin to. Ayan. Ito, bibilangin natin to. So, 5 plus 1 is 6. So, n plus 1. Then, what if naman po, kung hindi natin alam yung element ni array is 10 pala. So, 11 times siyang mag-ask ng condition, kaya pwede pa rin natin sabihin na n plus 1. Ang ilang beses naman po siyang nag-increment. So, nag-increment po siya dito from 1, 2, 3, 4, 5. So, 5 times po siya nag-increment, kaya pwede natin sabihin na n. Ayan. Dahil 5 times siya nag-increment, so what if naman po kapag yung number na element is 10? So, 10 times din po siyang mag-i-increment. So, let's proceed naman po dito sa sum is equals to sum plus ARRX index of I. Kung individual operation to the time complexity is 1, pero dahil nasa loop po siya, ilang beses siya na-execute. So, na-execute siya ng n times. So, 1 times n. Magiging n na lang po siya. So, kung babalikan natin yung rules, ang sunod na step is to add up the big O of each operation together. So, i-add po natin silang lahat para ma-compute natin. So, kapag in-add up po natin silang lahat, pwede tayong makakuha ng answer na 3n plus 3. So, after adding up, the next step po is to remove the constant. So, dito po, ang constant is 3. So, tatanggalin natin yung mga constant number and may iwan na lang po is n. So, ang last step is to find the highest term. Dahil nag-iisa na lang po si n, siya na lang po yung highest term natin since wala na siyang kasama. So, pwede nating sabihin na the time complexity of this algorithm is big O of n.
Now let's compute the space complexity. In here, we can see the variable and data structure that had been used in the algorithm. We have the ARRX, sum, I, and n. Here, we put the value of n, but in the given, we can see that it is 5. But in most cases, we do not know the value of n, so it's better to put n in the value. Next, sum, which has the value of 1, because here we can see in the given that the initial value of sum is 0. And in the given here, nag-update lang siya. So, it's 1. Then, sa I, just like sa sum, nag-update din siya and it is being used here. Then, lastly, n, which is used to know the value of array. And it is equals to 1. And if we add all of this, we will have the n plus 3. So, in order to get the notation, we need to take away the constant, which is the 3. So, we can say that it is big O of n.
Next is the asymptotic notation. Asymptotic notation are the mathematical notation used to describe the running time of an algorithm when the input tends toward a particular value or a limiting value. Example, the bubble sort when the input array is already sorted, the time taken by the algorithm is linear, or the best case. But When the input array is in reverse condition, the algorithm takes the maximum time to sort the element or the worst case scenario. When the input array is neither sorted nor in reverse order, then it takes average time. These durations are denoted using the asymptotic notations. There are mainly three asymptotic notations: the big O notation, the omega notation, and the theta notation. First, the big O notation. The big O notation represents the upper bound of a running time of an algorithm. Thus, it gives the worst case complexity of an algorithm. The graph expression can be described as the function f of n belong to the set 0 of g of n function. If there exists a positive constant c such that it lies between the 0 of cg of n for sufficiently large n. For any value of n, the running time of an algorithm does not cross the time provided by the 0 of g of n function. Since it gives the worst case running time of an algorithm, it is the widely used to analyze an algorithm as we are always interested in the worst case scenario. Next is the omega notation. Omega notation represents the lower bound of a running time of an algorithm, and it provides the worst case complexity of an algorithm. The graph expression can be described as the function f of n belong to the set omega of g of n function. If there exists a positive constant c such that it lies between the cg of n for sufficiently large n. For any value of n, the minimum time required by the algorithm is given by the omega of g of n function. And last, the theta notation. The theta notation encloses the function from above and below, since it represents the upper and the lower bound of a running time algorithm. It is used for analyzing the average case complexity of an algorithm. The graph expression can be described as the function f of n belong to the set theta of g of n function. If there exists a positive constant c1 and c2, such that it can be sandwiched between the c1 of g of n function and the c2 of g of n function, for the sufficiently large n. If a function f of n lies anywhere in between the c1 of g of n function and the c2 of g of n function, for all n is greater than or equal to n0, then the f of n is said to be the asymptotic type bound. And that's all for the time and space complexity in the asymptotic notation. I hope you like it and thank you for listening.